In this chapter, we're going to take a systematic look at the law of universal gravitation and its great applications. We have seen some examples of gravity. For example, when we stand on the surface of the Earth, we feel a gravitational pull towards the Earth. That is in fact due to the force of gravity between us and the Earth. But the force of gravity is a universal force that goes beyond the attraction between us and the Earth. That is to say, if you take any two objects in the universe, there is always a force of attraction between them, and that is called the force of universal gravitation. The discovery of the law of universal gravitation is one of the greatest and most important in the history of science. And there's a long story associated with that. And in this lecture, we're only going to talk about a very brief part of the history, very brief yet very important part of the history of the discovery of this great law. We start with the story of Johannes Kepler. Kepler spent many years observing the motion of the moon around the Earth and motion of the visible planets around the sun. And he summed up his great discoveries, his many years of observation, into three laws. Those so-called, known today as the Kepler three laws. They were published between the year 1609 to 1619. And we're going to study more about Kepler's laws in the next lecture, but let's first focus on the third of the three Kepler's laws, because it turns out this will be quite useful, quite inspirational for us to look at the law of universal gravitation. So let's look at what the third law says. The third law is also known as the law of periods. So Kepler discovered that if you look at the visible planets moving around the sun, such as Mars, Mercury, Venus, Jupiter, of course, Earth, and so on. If you look at the time it takes for that planet to go around the Earth once, that is, of course, known as a period. And in the case of the Earth, that is 365 days, known as a year. That's an Earth year. But in general, we call this time T, the time it takes to go around the sun once. We call it T. And then we also denote the orbital radius of a planet around the sun as R. Now, by the way, every planet doesn't quite move in exactly a circular orbital around the sun, but at least for the Earth, we can approximately think of it as a circular orbital. That is part of Kepler's first law. You will see that in the next lecture. But anyhow, you can, for simplicity, assume that a planet goes around the sun in a circular orbital radius R. Okay, so you have T and R. Kepler made observations for the values of T and values of R for the visible planets. And he found there exists an interesting relationship between T and R, known today as Kepler's third law. He found that T and R, they're not proportional to each other. However, if you raise T to the power 2 and raise R to the power 3, then you find that they are proportional to each other, meaning that for any of these visible planets that he studied, if you plot T squared versus R to the power 3, you're going to get a constant. Okay, there's a constant, and that constant we can call it K. And that K is the same for all these planets. That is known as Kepler's third law, the law of periods. Now, we all know that the law of universal gravitation is attributed to the great Sir Isaac Newton, the same person who gave us Newton's three laws of motion that we studied in chapter 5. And Newton famously said that he was able to achieve so much because he stood on the shoulders of giants, right? One of those giants got to be Johannes Kepler, because Newton certainly drew inspiration from Kepler's laws in his discovery of the law of universal gravitation. And in fact, if you really apply Kepler's third law as something you already know, you can really get a lot of insight into the so-called law of universal gravitation, which is the centerpiece of this chapter. So let's see how we can start with Kepler's third law and sort of deduce the law of universal gravitation. So Newton published his very famous book, the Principia. This is the Latin word for principle, okay? The so-called mathematical principle of natural philosophy, perhaps the greatest book of science ever written. That was the year 1687. In that book, he gave us Newton's 3 laws of motion, and he also wrote down the famous law of universal gravitation. And this is just one little one diagram, one page from that famous book. You can look at how complicated these diagrams are, and it's all written in Latin. We don't attempt to really use his original literature to state his famous law. Rather, what we want to do is we can look at how Kepler's third law can give us a lot of insight into the law of universal gravitation. Okay, so suppose you have 2 point masses. Okay, for now, let's restrict yourself to 2 point masses. The distance between them is r. So let's connect them with a line. We call distance r. This guy has a mass m1, and this guy has a mass m2. Now we suspect there's a force of attraction between them. How do you know the force is attractive? Because common sense, all these planets go around the sun, okay? And so the sun must attract each planet. Otherwise, how can they move around the sun in a circular or near circular orbit, right? It takes centripetal force to do that, and that's a force leading to the center of the circle, which is at the on the sun. So therefore, you got to have an attractive force, not a repulsive force. Okay, so how much is that attractive force equal to? How does it depend on M1, M2, and R? Well, one of the things we realize, going back all the way to Galileo's brilliant observation about gravity, is that everything falling under the influence of gravity near the surface of the Earth fall at the same rate, which means the acceleration of gravity is the same for any object, regardless of its mass. And if you combine that with Newton's second law, you realize that since the acceleration is the same, okay, F equals ma, right? F equals ma. And that a is the same for everybody. How is that possible? The only possibility is that the force is also proportional to the mass. Okay, in fact, we know the force of gravity is mg, near the surface of the Earth, mg. So here's a force that's proportional to the mass of the object that receives that force, right? No other force behaves like that. Gravity is the only force that automatically increases when the mass of the object subject to the gravitational force increases. It's proportional, okay? And because of that, when you double the mass, you also double the force applied. Therefore, the acceleration is the same. Therefore, everything falls at the same rate. And that also explains why, if you look at Kepler's third law, all these planets, they have different mass, of course. And yet, their periods and their orbital radius, that's Kepler's third law, t to the power 3 divided by r to the power, t to the power 2 divided by r to the power 3, that ratio has nothing to do with the mass of any planet. That k is the same for all these planets. Okay, so this also tells you that it's reasonable to assume that it's not just for the force, the gravitational force between the Earth and us. It's for any gravitational force. We can assume that F is proportional to the mass. Here, F from 1 to 2. Okay, this I denote the force from mass 1 to mass 2 as F12. Okay, we know it's proportional to M2. Right? We know, let's say M1 is the Earth, M2 is us, and then the force exerted by Earth on us is proportional to our mass, which is M2. That's from experimental observation. But at the same time, we also realize that it's got to be proportional to M1 as well. Why is that? Because there is also Newton's third law, which says that F12 has got to be F equal to F21. Okay? Newton, because it's action and reaction. But if F12 is proportional to M2, then by symmetry, F21 has got to be proportional to M1. But guess what? F21 and F12 are the same. That's Newton's third law. Okay, so therefore, the expression for the force between the two masses must be proportional to both masses. If it's proportional to one of these two masses, it's going to be proportional to the other one. Therefore, F21 and F12 will be equal to each other without violating Newton's third law. Okay, so that is quite clear. Now, how does it depend on the distance between them? Common sense tells us that the further the two objects are from each other, the weaker the force. But how does it depend on the distance? Well, we can think of, it's a reasonable assumption. At least it's one of the simplest assumptions, and that is you can think of a power dependency on R. So we assume it's divided by R to the power n. N is an unknown number to be determined. Okay, and it's going to be a positive number, and therefore, as you increase R, you're going to decrease the force, which agrees with common sense. Okay, can we find n? Turns out that actually can be done if you believe in Kepler's third law. Okay, now this is only a proportionality, and there's a constant of proportionality, of course, and that constant, I can give it any name. Why don't we just call it big G, okay? Big G. So with that in mind, I can now assume that the force between the two objects is equal to G m1 m2 over R to the power n. Again, this n is to be determined. Okay. Do not confuse this big G with small g. Small g is the acceleration of gravity, specifically on the surface of the Earth. Big G is a constant that applies to all gravitational forces. So it's a very different story. It's totally different quantities. Okay, now given this, how do we know this is right? Well, it's got to agree with Kepler's third law, which is from experiment, from observation, right? So let us assume this to be true, this expression to be true. Can we find n by applying this force to the study of the motion of a planet around the sun with the input of Kepler's third law? Well, let's see, right? You have a planet going around the sun. So here is, I'm going to draw part of the orbit of a planet. So here is part of a circle. Let's say this is the Earth, for example. Right? Here's the Earth right here. And it moves with a speed v. And it moves in a near circular orbit. For simplicity, it's just a circle. Okay, here's the sun. So here's the Earth, and here's the sun. Okay, the distance between them is r. And we assume r hardly changes because it's near circular orbit. So basically, the Earth is doing a circular motion around the sun. And therefore, there has to be a centripetal force, right? The centripetal force got to be pointing from the Earth to the sun, like this. Fc, right? But wait a second, who is providing the Earth with that centripetal force? Well, it's the gravitational pull from the sun to the Earth. So gravity provides the Earth with the centripetal force needed to move in a circle around the sun. That is the key idea here. Fg is Fc, okay? And Fg, as you know, is G, mass of the Earth, mass of the sun. I'm going to use small letter m for the mass of the Earth, capital letter M for the mass of the sun, and we're going to divide it by R to the power n. R to the power n here. Again, I'm going to use a different color. That's the variable I need to hopefully find out. And what does that equal to? That equals m, small m, v squared over r, right? Because that's, centripetal force, mass times centripetal acceleration, right? Now, Kepler's third law doesn't give you v, the speed, rather gives you the orbital radius and the period t to go around the sun once. So I'm going to rewrite v as distance over time. Okay, now over a course of 1 year, the time is capital T. The distance traveled by the Earth in 1 year is 2 pi r. So we have 2 pi r over t, okay, squared. All right, now you notice that the two small m's cancel out. Okay, so indeed, the period and orbital radius eventually this entire expression will have nothing to do with the mass of the Earth. That's why it's the same for all planets. The mass of the planet doesn't matter. But we can clean up the right-hand side a little bit. And so this is 4 pi squared all to the first power divided by t squared, right? Now, you know there's a t squared coming out, so I'm going to solve for t squared now. Okay, so move to t squared to the other side and move everything to the right-hand side. So it's 4 pi squared divided by gm times r to the what power? Oh, there's a power of 1 on the right-hand side. There's also r to the power n coming from the left-hand side. So overall, this is n plus 1, isn't it? Right? N plus 1. Now, can we find what n is? The answer is yes, we can. Look, this entire thing in the parentheses, it's just a constant, okay? G is a constant. M here is the mass of the sun, not mass of the Earth. So it doesn't depend on each planet, it only depends on the mass of the sun, which is the same for all these visible planets. And if you compare that with Kepler's third law, Kepler's third law says t squared equals a constant times r to the power 3, right? Look, Kepler's third law right here. Right? So what does that tell you? If you believe in Kepler's third law, you can compare these. Compare. What does that tell you about R? It says that n plus 1 must equal to 3. And R, therefore, equals 2. Wow, that is an important part of the law of universal gravitation. We have found by comparing our assumption with an observation known to be true, the Kepler third law, that the force of gravity between two objects goes down as 1 over r to the power 2. So when you double the distance between them, the force becomes 1/4 in strength. This is also known as the inverse squared law because r is in a denominator and it's squared. That's how the force of gravity depends on r. You will hear a lot of stories about inverse squared law. Turns out that even though we do not know for sure why nature chooses this special number of 2 here, right? This is n. Shouldn't call it r, n. Okay, n. We do not know why exactly nature chose this number 2 for n. We do know, as we will see later, that this is a very special number. Unlike any other number, this number 2 is not like any other number. It has profound consequences in both the gravitational force and the electromagnetic force that you will learn in a later course. Okay, so this is just a prelude of something very exciting to come. And it also says, tells what k is. So k, the constant, equals to 4 pi squared over g over m. So it really has to do with this constant. G also has to do with the mass of the sun. Okay, so we now have a full expression for the force of gravity, the universal force of gravity between two objects, F of g equals to g times one mass times the other mass. I can use m1 and m2 if I want to, divided by r to the power 2. That's the magnitude. Okay, that's the magnitude. And as far as direction, it's an attractive force. It's an attractive force. So it points from one object to the other object. Okay, it attracts them together. That is the expression for Newton's law of universal gravitation. There's a long and interesting history about who deserved credit to be the first person who realized that the force of gravity depends on 1 over r to the power 2. Newton claimed that he was the person who found it first, and then somebody else, this guy by the name of Robert Hooke, as in Hooke's law that you saw in chapter 12 of elasticity, also claimed that he was the first person who discovered it, and so on and so forth. But that's less important to us. For us, what we care about now is that the force of gravity is an inverse squared law, and you will see how important this observation is. Okay, and again, the direction is from one object to another, they attract each other. What is the value of G? Now, you know, it's common sense that if you believe that gravity is a universal force, that G's got to be very, very small in magnitude, in SI unit. Why? Because, well, you know, that would mean that you and I also have a force of gravity attracting each other, right? What if we're shaking hands, so the distance between us is under a meter, right? And it's under a meter, and you know, we can plug in our masses, you know, 50 kilograms, 60 kilograms, or whatever, right? And R is under a meter. If G has an SI unit value of 1 unit, okay, then you're going to get a ridiculously large force. 50 times 60 divided by something less than 1, right? You're looking at more than 3,000 newtons. That is ridiculous. The force between you and I is so incredibly small that we never notice it. The only time the force of gravity becomes significant is when one of these two masses, M1 and M2, at least one of these two masses become astronomically large. For example, the small m is our mass, big M is the mass of the Earth. And that is when the force becomes appreciable, and that is what? Our weight. Okay, so the universal gravitational force plays a dominant role in the large structure of the universe, how the Earth moves around the sun, how the moon moves around the Earth, and how we're stuck to the surface of the Earth, you know, how the galaxies are structured and so on. But it is only important for these astronomically large masses. Okay, the force between us and a mountain, between two skyscrapers, that's negligibly small, because this big G has got to be an extremely small number. And because of that, is one of the most difficult constants to be measured. And by the way, there are some constants that can vary from material to material. For example, spring constant of a spring, or you know, the Young's modulus of steel. If you change to a different material, the Young's modulus changes. But this G is known to be a universal constant. It's one of the few universal constants. It doesn't change from material to material. Therefore, it's got great importance. As a matter of fact, any formula that has to do with gravity has a big G in it. It's not small g, okay? Small g has to do with, you know, the gravitational attraction between us and the Earth when we stand on the surface of the Earth. So it's a very special case. And it's an acceleration. Big G is not even an acceleration, but it's a universal constant. Again, it's going to be very small. It's the first universal constants we have learned in the Physics 8 series so far. You will learn some more constants, and you know, there are not a whole lot of them. Each is of tremendous importance, and this is the first one. Okay, so how do you measure something that small? You know, if you look at, for example, the gravitational attraction between two steel balls, even if each one can weigh, you know, can have a mass of say 50 kilograms, and you separate them by 1 meter, you know, the force between them is extremely small. So how do you measure something that small? Well, it would take a genius to come up with a precise measurement. And even though this Newton's law of universal gravitation was published again in the year 1687, see here. Okay, the first successful measurement of the universal gravitational constant, big G, with an error of under 1% was achieved in the year 1797 to the year 1798. That is over 100 years since Newton made his major discovery. Okay, and that is known as the Cavendish experiment. It's an ingenious method that we still use today for measuring certain small quantities, certain small displacements. This, the picture on the left-hand side is a depiction of Henry Cavendish's original device to do the measurement. And the diagram on the right-hand side is a simplified version that illustrates the basic idea, okay? I'm not going to get into too far into the details, but the basic idea is this. You have a pair of heavy masses, okay? It could be made of gold, it could be made of lead, something heavy, okay? Something heavy, all right? So you originally they're here and here, okay? And you connect them with a rod and you suspend the midpoint of the rod right here with a thin cable from the ceiling, okay? Here's a ceiling right here. Now, imagine this. Imagine that I bring in a pair of heavy masses, this guy and this guy, all right? One close to this sphere, the other close to that sphere. Now, there is a attraction between each pair of small mass and big mass, right? So as a result, you can imagine, at least in principle, you can imagine that this red sphere is going to move a little bit towards this direction. That one is going to move a little bit toward that direction, right? So therefore, this arm connecting the two red balls will rotate. But of course, by an extremely small angle, right? Question, how do you measure such a small angle? Well, the idea is to use a mirror mounted on this setup, and then you have a beam of light that you project onto this mirror, and it bounces back, okay? Now, even if the mirror turns by a tiny, tiny angle, if each beam travels a long distance, then the reflected beam can move appreciably if the mirror turns only by a small angle. So this angle is extremely small, but I can make this arm very long. So here is where the reflected beam will show on, project onto the wall, for example. If I make this distance extremely long, then even for this very small angle, I can see an appreciable motion of this reflected dot on the wall. Okay, so that's the basic idea. And we use that to measure, for example, Young's modulus, in this Young's modulus experiment. That's what we did. Okay, but the Cavendish experiment was far more difficult because we're dealing with an extremely small amount of rotation. And also back at that time, he didn't have anything, a good light source like laser, for example. So it was a very difficult experiment. That's why it wasn't achieved until over 100 years since Newton published his original discovery of the law of gravitation. But today we know what the value of G is, okay? G is approximately 6.67 times 10 to the negative 11 in SI units. Look at how small this is. What is the unit of G? Well, you don't have to memorize this. You can just find it from the formula right here. Just solve for G from this formula. You have Newton times meter squared over kilogram squared, right? So that's how we can find the unit of Newton meter squared over kilogram squared. Now, Newton is a derived unit. So Newton itself is kilograms meter per second squared. So you can plug that in and you get kilogram, and you will get meter to the power 3 divided by kilogram and divided by second squared. I mean, you can do, if you want, you can always do that. Okay, but this what we wrote is also correct. At any rate, you're looking at an extremely small value. It's again the first fundamental constant we have learned in this course, and you only learn a few more. There are not a whole lot of them, and each one of them will have extreme importance. If I change any of these values by a very tiny portion, the universe that we see today will be totally different. All right, so this is the basic introduction of the law of universal gravitation. And what we're going to do is, starting from now on, we're going to apply the law of universal gravitation to study a variety of cases, from motion of planets and satellites to what happens on the surface of the Earth, known as terrestrial gravity. Okay, so the next lecture, we're going to first apply the law of universal gravitation to visit Kepler's 3 laws, even though historically Kepler's 3 laws were discovered before Newton's law of gravity. Now that we know Newton's law of universal gravitation, the Kepler's laws can each be derived from the law of universal gravitation. So we see that in the next lecture.